Hello guys, this is Josh again, and today we're going to start talking about quantum mechanics. This is going to be the first lecture in our series over here on quantum mechanics. Now, the way I'm thinking about doing it is similar to how MIT does it, in that I want to make 3 different series for quantum mechanics: quantum mechanics 1, 2, and 3. And we're going to progressively get deeper and deeper into real quantum theory, and the material is going to get harder too. But right now, quantum mechanics 1, this is the first lecture. We're just going to learn basic quantum mechanics, wave functions, expectations, all that jazz. And everything we're going to build upon in this course is what's going to be covered more deeply in the next course and then in the last course as well. As a prereq to this course, you should have seen or have knowledge of classical physics, because quantum mechanics is ultimately a correction on classical physics. And I have a course on classical mechanics on the channel as well, and also E&M, electricity and magnetism. That's going to be important too when we talk about light, specifically photons of light and waves and polarizers. So you should have a good knowledge of like the energy density due to an electric field. Okay, so these are the 2 main prereqs, and of course calculus and all that jazz, linear algebra. But I'm sure you guys, if you know classical physics and E&M, you'll know linear algebra and calculus as well. Okay, so today in the first lecture, all I want to talk about is the need for quantum mechanics. Why is this such a deep theory, and why is it so needed? Like, why can't we just describe the world with Newton's laws, you know? So what we're going to talk about first is we're going to split it up into 4 different things, okay? Or maybe 3. So what I really want to talk about first is linearity. And this might be like, why are you talking about linearity? But it's going to be very important later, as I'll talk about. After linearity, we want to talk about complex numbers, okay? Right now, you might think these are completely unrelated, but complex numbers. But I'll show you why they're so important. After complex numbers, I want to talk briefly on need for quantum mechanics, or the loss of determinism, which we will see what that is. Loss of determinism. And then lastly, I'm going to talk a little bit about superposition. And hopefully after today's lecture, you're going to get a feel of what quantum mechanics is at its core and the real need for it. Okay? But without further ado, also I hope you guys like this, this background here. I kind of like it, to be honest. But anyways, let's get right into it. Number 1. So, quantum mechanics. We know that every single discipline in physics tries to describe the underlying world. The whole point of physics is to describe, to model phenomenon that's going on, to try to best understand the world. Newton, in his Principia, he described classical physics, the physics of macroscopic objects, right? And classical mechanics, as we will see shortly, is inherently a nonlinear theory, okay? And I'll explain what that means. Now, then came Maxwell with his electromagnetic theory, Maxwell's equations, right? And this is describing the fields, the electric and magnetic fields, while classical mechanics, Newton's law, tries to describe the gravitational field. E&M describes the electric and magnetic field. Maxwell's equations describe these 2 fundamental forces in nature. Then you have the strong force, you have the weak force, and their respective fields, right? But so it turns out that electricity and magnetism, Maxwell's equations, are inherently at its core, it's a linear theory. And as you might have guessed, linear theories are much easier to work with than nonlinear theories, okay? And what do I mean by linear? Okay, so this is what I mean. A linear operator, a linear equation, a linear differential equation is of the form this. So a linear equation looks like this: LU equals 0, right? And U is some unknown variable, okay? It's also known as the dynamical variable of the system. And this is the variable that tells us the dynamics of the system. That's why it's called a dynamical variable. It is our unknown, and it is what we're trying to solve to see the behavior of the system. Okay? And L is, as I said, the operator, the linear operator. And I'll go into a little more detail on what that is right now. So a linear operator, at first let me give you an example of a linear differential equation. This might seem a little vague to you right now. So an example of this would be, let's say I have something like this. du dt plus 1 over tau u equals 0. This is a linear equation. Why? Because you can see that we can pull this d dt plus 1 over tau out, and then just multiply this whole thing by u, and that equals 0. And this guy would be our linear operator L. Now, what is a linear operator? Well, what is linearity? A linear operator satisfies two constraints, or two axioms, you can say. So if you apply the linear operator on alpha u, where alpha is just a real number, this will give you alpha times Lu. Okay, that's definition 1. And alpha is going to be a real number. Number 2 is that the linear operator acting on u1 plus u2, since it's linear, you can actually separate it, so it's just Lu1 plus Lu2. So these are what I'll call some axioms of linear operators. If you have an operator that satisfies these two rules, you can say, then it is a linear operator. Okay? Now, why are these linear operators important at all? Well, okay, so electricity and magnetism. What are our unknown variables? Well, what are our dynamical variables, let's say? Well, one of them is definitely the electric field. One of them is the magnetic field. We have also the charge density, rho, and also the current density, J. So this is electricity and magnetism. Okay? So these are our dynamical variables, and these 4 variables, they solve Maxwell's equations. Now, I'm not going to write them out, but they solve Maxwell's equations. And at its core, Maxwell's equations are linear equations for these 4 unknown variables. Okay? Now, classical mechanics. Why did I say before that it was a nonlinear theory? Well, as we all know, classical mechanics, Newton's laws is just F equals ma, right? F equals ma. Now, how can we write this a little bit better? Well, assuming that the force can be derived from some potential function, like if it's a conservative force, then we can write the force as the negative derivative of the potential, right? Potential energy. And this is equal to mass times acceleration, and acceleration is nothing more than the second derivative position with respect to time. Okay, now you see the problem is that, well, the derivative is linear. It's a linear operator, because you can just split this up. If you have a derivative of u1 plus u2, from the properties of derivatives is just derivative of u1 plus the derivative of u2. But so that's a linear operator. But the potential, the derivative of the potential, it can be very nonlinear. And this is what makes classical mechanics really hard. For example, the potential can be a cubic, right? It could be a quadratic as well, harmonic oscillator potential. And its derivative would be that. So this is a very nonlinear theory. And adding on top of this, general relativity. General relativity basically boils down to Einstein's field equations, which look something like this. So 1/2 r g mu nu equals 8 pi t mu nu. Now this is inherently a nonlinear theory, and even so, this is a highly nonlinear theory. In our course on general relativity, we're going to go extremely in depth about this, but just know for now that it's a very nonlinear theory, and this is even a tensor equation. It's not a classical differential equation. So this is what makes me very complicated. Now, on the flip side, quantum mechanics. Quantum mechanics, our dynamical variable is what is known as the wave function, and we denote it by psi. So this is the wave function. Okay? And psi satisfies the famous Schrödinger equation that Edwin Schrödinger managed to devise in, what is it, 1920s, something like that. But the Schrödinger equation looks something like this. It's going to be IH bar d psi dt equals H psi. Now H is what is known as the Hamiltonian. And the important thing to know right now is that the Hamiltonian is indeed a linear operator. We'll show that it's a linear operator later, but right now I'm just giving it to you a priori. So this is indeed a linear equation. Why is it a linear equation? Well, you can see that we can rewrite the equation like this. IH bar d dt, right? And then minus H hat. And hat just designates an operator in quantum mechanics. So this times psi equals 0. This is exactly in the same form as L psi equals 0. So it's a linear equation. And because it's a linear equation, the Schrödinger equation governs the dynamics of a quantum system. And since it's a linear equation, this greatly simplifies the theory itself. And as you'll see when we work through quantum mechanics, all the different eccentricities and like mathematical theory behind it, you're going to see it's much easier than classical mechanics. When we were studying orbits, we were studying the 2-body problem, 3-body problem, n-body problem. Quantum mechanics is much easier in that regard. Okay, so that's the first main point here, linearity. It's going to pop up again and again and again. Second point, complex numbers. Okay, let me scroll down a bit. Complex numbers. You see from the Schrödinger equation, you have this I in here. Now, in classical mechanics, we use complex numbers to help us out, right? It wasn't really needed if we didn't want to use it. So in classical mechanics, complex numbers, we can write it like that, are used as to simplify, as a tool, I should say, are used as a tool to solve problems, right? If you can think about all the times you've used complex numbers in classical mechanics, they weren't really needed in the sense that they are in the Schrödinger equation. We just use them to solve problems. But as you can see in quantum mechanics, the Schrödinger equation, complex numbers are inherent, okay? They're inherent in the dynamics of the system. Dynamics of the system. Again, this I is a complex number. I is equal to square root of -1, right? Everybody knows this. But they're inherent in quantum mechanics. The wave function itself is a complex number. And this is very easy to see because you can see over here, the left-hand side of the Schrödinger equation. Let me just write, this is the Schrödinger equation. Okay? Now, the left-hand side is complex, it has an I. But the right-hand side has just H psi, right? So if the wave function was real, then you would have a real number on the right side and a complex number on the left side, and there would be some kind of contradiction. So at its core, quantum mechanics at its core, the wave function, the dynamical variable governing a quantum mechanical system, is complex in nature. Okay, and that's the big distinction here. So here we go. Complex numbers. This is why complex numbers are so important. And before we move on a little bit, I'm just gonna talk about some of the properties of complex numbers because they're gonna be useful later. Okay. So we all know that I is equal to square root of -1. We can write a complex number. We usually write a complex number z equals a plus bi, where a is the real part of the complex number denoted by real part of z, and b is also the imaginary part of the complex number, again z. Okay, now the magnitude of a complex number, denoted as z bar, between it's like the absolute value, it's also known as the modulus, is going to be equal to square root of the real part squared plus the imaginary part squared. And following from this, the magnitude squared of a didn't really write that good. So the magnitude squared is just a squared plus b squared, right? And it's also equal to z times z complex conjugate, where the complex conjugate of a complex number is just a minus bi. You just flip the sign between the real and imaginary parts. And you can easily see that the z times z bar is a squared plus b squared. Alright, that's about all we need for complex numbers. So hold on to that, and now let's go to laws of determinism. Okay, so this one is going to be a little bit more tricky, but I think we can do it. Let me just make some space over here. Okay, so number 3. What do I mean by laws of determinism? I haven't told you yet really how quantum mechanics works and why is it so weird, okay? So let me give you an experiment, for example. By the way, before we talk about this, quantum mechanics was really born with Planck. And Planck did a study of black body radiation. And he found that inherently the Planck's constant, h bar, was needed as a unit of measurement. And Planck's constant is a very small number. It's on the magnitude of 10 to the negative 34. And it turns out that h bar is so fundamental to quantum mechanics that by studying this black body radiation, he found that it was actually a whole new field was emerging. And then later, in the early 1900s, Einstein was working on the photoelectric effect. And he saw the need to he saw that light is actually made up of photons and their quanta, the quanta of light, the photons. Okay, and that's where that word quantum comes from, quanta. And he actually won the Nobel Prize for this. But that's just a background. But anyway, so consider this. Let's say I have some kind of polarizer. Okay, and what basically a polarizer does is, all it does is it has an input, some beam of light, and it has the polarizer. So this is a polarizer. Polarizer has some kind of direction. Let's say that the direction was this one. Okay, so the polarizer has some kind of axes, x and y. And let's say right now it's oriented in the x direction. So all the light going into the polarizer, since right now all the light is going in the x direction, all of the light is going to pass through. But for example, if we had light going from the y direction and it goes through the polarizer, well, nothing is going to go through, right? Because the polarizer is in the x direction. Polarizer, what it does is it filters the light, right? So, okay, now consider this. We all know that, as I said, Einstein showed, so 1900s, physicists showed that light is made up of quanta of photons, right? And light is this electromagnetic wave, but photons are particles, right? So we have this thing called a wave-particle duality going on, where on the one hand, light is a wave. It's just an electromagnetic wave, right? You know this from electricity and magnetism. Light is just a wave. But on the other hand, we know that light is made up of these quanta of photons. And photons are fundamental particles. So we get issues here. And how do we get issues here? Well, okay. Let's say we have an electric field. Our electric field is, let's say it looks something like this. E naught cosine alpha in the x direction and E naught sine alpha in the y direction. Okay? So we have this polarizer again, and it's polarized via this electric field. It's going to be polarized at an angle. So this angle is, oops, it's alpha, right? And we still have this polarizer. So the problem is this. We have light, sorry. The polarizer is still in the x direction, but the light is coming in at an angle alpha due to this electric field. So we have light coming in like that. Okay, now the problem is that so from electricity and magnetism, you know that the energy of an electric field, of the electron field, is going to be proportional to the magnitude of the electric field squared, right? So in this case, it will be proportional to, what would it be? It would just be E naught squared. If you take the square of the x part and the y part, you just get E naught squared. But now, after the light goes through the polarizer, the energy is going to be proportional. So after the polarizer, you only get the x component, right? So after the polarizer, E is just going to be E naught cos alpha I hat. So now you see that the energy is proportional to E naught squared, E naught cosine alpha, or rather squared. So the fraction, you actually have some energy loss, right? From the polarizer is actually going to absorb some energy. And this fraction of the energy loss is going to be equal to, well, it's just going to be equal to cosine squared alpha, right? And we can see this pretty easily, because let's say alpha was 0. If alpha is 0, then all of the light is going in the x direction, so the fraction of energy is going to be the same. It's going to be 1 because the polarizer is not really absorbing any energy. But let's say alpha is 90 degrees, that means we have light coming in the y direction, and then the fraction is going to be 0, which means none of the light is going through, and the energy is all lost, absorbed by the polarizer. Now, why am I talking about this? You think I'm going crazy, right? Well, I just said that light was made up of photons, right? So you're telling me that I have photons going into this polarizer, and some of them are leaving, and some of them are not leaving. Now, how is this possible? Photons are exactly identical, right? Photons are identical. They're particles. Electrons are identical. Photons are identical. Particles are identical for all intents and purposes. So what I'm basically telling you is that I'm sending in photons, identical photons, and some are leaving and some are not leaving. Do you see the contradiction there? If they're identical, what's to say that they shouldn't all leave? Okay, and this was a big question. This was a big question during that time. And people came up with crazy theories like the polarizer is oriented in such a way that depending on how the photons hit the polarizer is what makes them absorbed or not. But these ideas are, they don't answer the question at the fundamental level. At the fundamental level, what says if a photon goes through or if a photon gets absorbed is a probability. And this is where we get our main point, the loss of determinism. Because in the quantum mechanical world, we can't determine anything for sure. We have these photons going in, and there's a probability that they pass through in the x direction, and there's a probability that they get absorbed. We do not know for sure if the first photon going in is going to get absorbed or that it passes through. We have no idea if the 534th photon is going to pass through or get absorbed. All we know is that the fraction of photons that pass through in the x direction. Okay, and to shed a little bit more insight on how this works is that the photon has what is called its state. Okay, so state, wave function, you can write it WF, or it's also called a wave function vector. They're all the same thing, and they just denote the state of our system, state of the photon. And in this case, we can write the state of the photon like this. Okay, and this notation is we'll talk about a lot more, especially in the second course, is called bracket notation. Okay, this is just a handy notation. It was made by Dirac in the 1920s, I believe, and it's just a way to describe the state of a quantum mechanical system. If we treat light as an electromagnetic wave in the classical sense of E&M, then we get the wave from this electric field. As we all know, we know that E is equal to the energy of the wave of the photons equal to hf, or h nu rather, where nu is the frequency, and then we also know that lambda nu equals c. And that's how we can kind of find the wavelength of the light. And this all relates back to the electric field. Because remember, the electric field, the energy of the electric field is proportional, the energy of the field is proportional to the electric field squared, the energy of the light, sorry. And as I just said, that the energy is proportional to the wavelength. So this is the classical sense. We treat light as a wave. But we just saw that this comes into contradiction when we think about light as a photon. So we have to talk about photons in terms of their states. State is basically like the configuration of the system. Now let me give you an example of that. So let's say all the light was coming in as it was in this example, all in the x direction. Instead of thinking it as a wave, we think of it as photons, and photons are going to be characterized in that case by their state, which we write as photon in the x direction. Alright, and more generally, when light is coming in at an angle alpha, we say it is a photon in the alpha direction. And just as we wrote the electric field having a component in the x direction and a component in the y direction, the same thing we can write for a photon. We can say that the state of the photon is actually a superposition of its state in the x direction plus its state in the y direction with appropriate weights. Okay, just like that. And then what dictates how much photons go through in the x direction and how many photons get absorbed is these exact weights here. We'll see later that these weights are actually the probability amplitudes. So probability amplitudes for going into the state x and into the state y. So we can already see the inherent differences between quantum mechanics and regular E&M and classical mechanics. Here we have a complete loss of determinism, as I said. We're dealing in terms of probabilities now, a probability to get through. And we know that the probability is cosine squared alpha in this case, but we do not know for sure. It cannot be physically determined unless we make a measurement, right? If each individual photon has passed through or gone absorbed. So that is the inherent difference. So that's number 3. And then the last one that we're starting to talk about now is superposition. And superposition honestly is a weird concept because it's completely different than anything you're used to thinking about. And the first case I can talk about is what we just said, as the photon in the alpha state. It turns out that the photon in this angle alpha is a superposition of its x state and its y state. But okay, that might not make so much sense to you, so let me think about something else here. So as you guys know, there's this famous thought experiment, Schrodinger's cat, right? Schrodinger's cat. Now what Schrodinger's cat basically is to the layperson is that you have this box and you have a cat in this box, right? And, I don't know, I'll just draw a person. And it is said that this cat or this human or whatever is actually in the box and out of the box at the same time. It's in a superposition of being in the box and out of the box. And the only way you can tell if it's actually in the box is if you actually open the box, i.e. this is making a measurement on the system. And when you open the box, you can only know for sure that if it's in that state in the box or if it's actually out of the box. So in that way, a person or a cat is in the superposition of in the box and out of the box. But even on a deeper level, we can consider an electron. Let's say electron. So an electron, a particle, of course, as you guys know, but inherently, even if an electron is stationary in space, it could have a spin, okay? And we'll talk about this a lot more later, but let me just tell you right now that it has a spin. And this spin can be in any direction. Right now, let's say that the electron has a spin in the z direction. So we can say that the state of the system is that we have an electron that's spin up, which we write as just an up arrow, very original, I know, and in the z direction. So that's the state of the system. It's an electron with spin up in the z direction, okay? And spin basically is its intrinsic, so spin is essentially its intrinsic angular momentum. So intrinsic angular momentum. Every time I try to explain this, I always like to give a good example of the Earth around the Sun. We know that the Earth revolves around the Sun with its angular momentum, its orbital angular momentum, usually denoted like L or something. But also internally, it has its own intrinsic angular momentum. So you can think of an electron like this. Even though it's stationary in space, it still has an intrinsic angular momentum. You can think of it as it rotating with some angular velocity omega. Okay, but on the other hand, we can also have an electron with spin in the negative z direction, right? So this would be denoted by this, spin down in the z direction. Now we can make a general state of a quantum system. Remember, if spin up is a solution to the Schrödinger equation and if spin down are both solutions to the Schrödinger equation, we know that quantum mechanics is a linear theory. So any linear combination, alpha up z plus beta down z, is also a valid state. So we can make any wave function as a superposition of up and down states. This is where linearity comes into play a lot, and it's exactly what we're going to use when we solve the Schrödinger equation. We're going to get one solution, maybe this, another solution, maybe this. So the most general solution is going to be a superposition with coefficients alpha and beta that are both complex, and this is going to be our most general solution as a superposition. Okay, and if we make a measurement on the system, so any measurement on the system, let's say we have our eyeballs and we look and to see the spin of the electron somehow, some experimental technique, and we see that it's in the spin up state, then the wave function collapses to this up state, okay? With probability equal to, or it's proportional to alpha squared. Okay, so these are basically the weights. Now, okay, this is known as the collapse of the wave function. So let me just write here collapse. And this is a pretty strange phenomenon. This took me a while to like really sink in the first time I learned it. You have this general state psi. It can be a superposition of any states. In general, it could be a superposition of any coefficients times any states psi I. Okay? And when you make a measurement and you find it to be it's in the up state, it immediately collapses to that state with probability proportional to the square of the coefficients. So this is what we mean by superposition. We can write a state of a quantum system in terms of many basis states. In the photon case, in the case of the light going through the polarizer, our photon, when it's at some angle, we can write it as a superposition of the basis states in the x and in the y direction. And when we send it through the polarizer, since the polarizer is in the x direction, only this state goes on, okay? With probability, of course, cosine squared alpha, as you can see here. Okay, so One last example I want to talk about is what is known as the damn, I forgot its name. Oh geez, hold on. But yeah, it's the Sterngerlach experiment. Sterngerlach experiment. So these were some experimenters in the 20s, I believe, also. And what they basically did was, okay, they had an oven, right? And this oven had a small hole in it. And they had silver atoms in this oven. So silver atoms. And this oven, it heated the silver atoms and then spit them out through this small little hole. And then after that, it went through a little collimator just to smoothen it out. I really don't even know what the collimator does, to be honest. But then it goes through a inhomogeneous magnetic field. So the magnetic field can look something like this. We get this part over here, and then we have this flat rectangular part over here. So this is a B field. And as you know, if you have an electron going through, if you have some atoms going through a magnetic field, they are going to deflect. And that's exactly what they did. Okay? And then there was some kind of screen over here that can measure the deflections. So it's gonna pop up everywhere that they deflect. So inherently, an electron has a magnetic. Oh, also they use silver because silver has only one outermost electrons. So you can say that everything else is irrelevant because they all cancel out with the proton. So that's all neutral. And then you're just left with that one electron on its, I believe it's in its 5s orbital. But that's regardless of the point. The magnetic moment of the electron is proportional to its spin. Okay? And in a magnetic field, the force imparted on some mass, electrons have mass, so the force imparted is proportional to the derivative of the magnetic field. And in this case, it's in the z direction. So we would expect a continuous distribution of spots on this screen as a result, because since the derivative of magnetic field is going to be varied from point to point, we expect the spins, the magnetic moments, also to be varied, and as a result, the location on the screen. But what we see is that we only have two areas where it hits, right here and right here. And what this tells us is the magnetic moment takes one of two values. It's either up or down. If we call this up, that's up, and that's down. So this Sterngerlach experiment showed the necessity for a completely different theory than classical physics, in that the magnetic moment is either up or down, and it's not a continuous distribution, as classical mechanics would show, because of the continuous magnetic moments that it predicts. So what this showed is that since the magnetic moment is what is known as quantized. Quantized means it takes on a discrete value, discrete set of numbers. Since the magnetic moment is quantized, the spin is also quantized, which we just talked about, up or down. Okay? And electrons are what are known as spin 1/2 systems, and they exhibit this two-state behavior. Okay? Two-state behavior. So I hope that gives you a good understanding of how and why quantum mechanics is so different, and also why we really need it. Like, if honestly, if it wasn't even needed, I wouldn't be talking about it, okay? But it's inherently, it's a theory that needs to be done to explain the world. And classical mechanics is not a good way of explaining subatomic particles. And that's why we need quantum mechanics, okay? So that's it for the first lecture. We have a good foundation of why we need quantum mechanics, of how different quantum mechanics is. We talked about linearity. Quantum mechanics is inherently a linear theory. We talked about why complex numbers are needed, that they're in the Schrödinger equation themselves, that the wave function is of complex nature. We see how we lose all signs of determinism. We can't really determine anything for sure, only probabilities, and these probabilities add up, they superpose together with different states to make a general state of a quantum mechanical system. Okay, and we're going to get a lot more in depth into a superposition in the next lecture. So if you're really kind of like fuzzy about that, I would suggest maybe Google it a bit, but we'll get more into it next lecture. Okay, so see you then.